I guess we'll just get started. Should we start the clock or let it go? Okay. Welcome. This is a talk on big data as a service. My name is Tom Phelan. I'm the chief architect and co-founder of Blue Data. My co-presenter today is Chris Applegate. We're very lucky to have him. He is a cloud and big data storage solutions architect for Dell. And I think it's actually very topical that we have this talk today. If you attended Rob Bearden's keynote this morning, he covered a lot of the same sorts of themes that we'll be talking today, but he covered them in terms of software, and we'll be talking more about infrastructure and the evolution of how infrastructure has played a part in the evolution of Hadoop and big data as a service. A quick agenda is we'll talk a little bit about the history of Hadoop. It's always good to know where you started to find out where you'll end up. We'll talk about the changes in hardware with storage acceleration and network acceleration. Then talk a little bit about what it means to have virtualization and how that has impacted the delivery mechanisms for Hadoop. And finally, we'll get into some more detail about what big data as a service really is. There's a large question about what it's actually defined as. We'll try to narrow that down. Then we'll talk about the various trade-offs between public and private clouds. We'll have some time for Q&A at the end, so we'll try to wrap this up in about 35 minutes to leave some time. So let's begin. As we know, we learned this morning, this is the 10th anniversary of Hadoop. In fact, Hadoop probably started a little bit earlier, probably started 13 years ago, by our reckoning, back when we had this dinosaur-looking elephant rather than the nice elephant that we see today. And as it started with a Google file system paper in 2003. And this paper was a kind of a seminal event for its day. Google was having a problem and they needed a solution. They had a large amount of data and they needed to process it in batch mode, but still relatively quickly. At that time, they were hampered by what was available as hardware infrastructure. They were limited to 1 gigabit Ethernet. That was as fast as you could get in a data center. That drove a lot of their design choices. Similarly, what was available at the time was enterprise-class storage devices. Those tended to be proprietary, expensive, and require expensive infrastructure, such as fiber channel, to deliver the data. At that time, applications were pretty much bringing the data to the compute. Google turned this on its head with its paper and said that why don't we instead bring compute to the storage? And here we have these local, cheap, relatively fast for their day, high-capacity storage devices, and we don't really care about all these enterprise features like geographical replication or snapshotting. All I need is a fast, low-cost, more or less reliable storage mechanism. That was the beginning of HDFS and Hadoop. But times have changed since then.
So again, rewind your brains back to 2006 and realize what was going on in the industry, right? On the compute side of the house, we at Dell were making highly consolidated servers, blade chassis, starting the initial steps down to converged architectures. Things were getting really complex and pretty siloed. You put your compute in a silo here, and then you do the same thing on the other side with either NAS or SAN, some technology like that. And they would really keep them completely separated from each other. When we talk about any type of distributed processing, we talk about round trip time and latency between them. Right? And so every time you're communicating between these two, you'd have some sort of service bus between them, and introducing any type of latency in that decreases latency exponentially as you scale it out. Right? So the idea here behind many of the distributed architectures was why not couple those two together? And what's the fastest, the lowest latency that you can actually bring between those two components? Put them inside the same box. Right? So this was a trend that we started to notice as a hardware manufacturer. We have our general purpose servers that I'm sure many people are familiar with here, many folks are running. Right? But we also cater to an elite group of folks. Right? These are people that we build custom servers for. These are our top elite customers that buy by volume. And one trend we started to notice was they started to kind of stray from the pack. They started to say, no, don't give us 8 servers inside 2U. Give us one server with lots of local disk. And we'll say, But what? We've been spending the last 5 years pulling local disk out of these servers so you can put them in the SAN. And they started to reverse that trend. We took those lessons learned, and we realize now that that was the early stages of a lot of the companies that were building the first Hadoop clusters, first Cassandra clusters, a lot of that technology. And we bring that down into our general purpose portfolio so that everybody can take advantage of that. And you look at our 12th generation, 13th generation servers, and on forward, you're going to start to see that trend of enabling things. Hadoop was really there first, but now we look at software-defined storage and a lot of those other, folks that are following on, they're going with the same type of paradigm shift where you bring lots of local storage, introducing a caching layer, et cetera. We talked a lot about compute and storage, but the same thing happening on the network side. Right? I remember when we first started building our our Hadoop solutions, we were doing, bonded 1 gigabit, 2 bonded 1 gigabit, right? And then after about 6 months, in our solution, we'd go to bonded 4, and then on up. As the cost per port dropped, we'd start to get 10, and bonded 10s is kind of where we were at about a year ago. But now Hadoop is actually starting to push the trend of some of the first customers that are talking to us about putting bonded 40 gig or bonded 100 gig inside their servers are the Hadoop folks. They're pushing that trend, right? Because that cost per port is falling drastically, right? And Hadoop is becoming more of a first-class citizen in an enterprise workload, and it has to be treated such, right? The other thing that came, kind of incorporated into the perfect storm are compression algorithms, right? Anytime you start dealing about compression, it's about the payoff between speed and capacity reduction, right? And so it's all about finding that happy median. Right? Just about that time, we started to see things like LZO and Snappy ultimately that provided the best balance between speed and actual compression effectiveness. So,
okay, thank you. So I thought I'd move forward a little bit now. So a number of years have passed. We've improved the storage architecture, the network architecture, and we start to see papers like this one. This is from AmpLab at Berkeley, where they're starting to say disk locality is no longer an issue. So it's no longer necessary to co-locate compute and storage. There are similar papers from Microsoft Labs and from IBM as well. So there's a series of these papers taking place. But what does this really mean? Are we saying that disk locality really is less relevant? Well, in fact, it is. So disk locality is starting to become less relevant because of the faster network architecture, because of intelligence built around caching, tiering architectures that are now available. One example is Luxio, formerly known as Tachyon. They have a distributed caching system, which can be built on top of multiple tiers of more or less persistent storage, RAM, SSD, and then spinning media. What that allows us to do is say, though, even though disk locality is no longer a factor, data locality is still a very great big factor in terms of performance with Hadoop. So you want to make sure that when it's time for your MapReduce job or your Spark job or your HBase job, that data needs to be very near the processing engine, probably on the same physical box. But if you can prefetch it, if you can store it intelligently, it doesn't have to reside on local disk. It can reside somewhere else. Therefore, we end up with compute and storage separation. That's what we have today. And we do that with still performance. You could do that in 2003, but you wouldn't get any good performance. Now, technology has advanced where you can do that with sufficient performance. Now we start to talk about how this technology was the first step on our road from Hadoop on bare metal on-prem to potentially Hadoop and big data as a service in the cloud. So the next big piece is virtualization. Now, it's not absolutely required. You could do everything automated and flexible and somewhat elastic using bare metal hardware. You'd have a team of people that would be running around the IT department that would do this. But in a real sense, in any sort of practical sense, you have to have some sort of virtualization technology in order to automate this successfully. Now, that's good that we had the virtualization revolution during the 2000s. So VMware started it with ESX and then Hyper-V from Microsoft. And then, of course, we had a whole bunch of other people. Now it's OpenStack with KVM. We have some Xen. Those were all hardware hypervisor solutions. And Chris will talk a little bit about those technologies.
All right, so again, remember, just like we see with big data now, we see those disruptive technologies, back then. Back in the 2000s, it was virtualization was big. We started to see customers invest in things like VMware, Hyper-V, et cetera, and we still see that same trend today. So what is it that virtualization brings that you previously didn't have? Right? It provides an additional infrastructure, right, to allow you to introduce additional layers of automation. It makes things much more flexible, allows you to consolidate things, oversubscribe things, and gives you that ability to have elasticity, right, that you didn't previously have with the hardware layer, right, a pure hardware layer. It allows the cost reduction, moving out of warranty servers into a complete VM, and all those type of things. I mean, the things that we were all taught to spout during people that were considering virtualization for the first time. And then multi-tenancy. We see the same thing with hosting providers, cloud providers. We're able to put multiple customers on a single stack and maintain some level of security. And we're not talking just data security, but also security in isolation from noisy neighbors, right? Resource security, guaranteed access to resources, et cetera. And then fault isolation, keeping failure domains to the tenant local. Right? This is a lot of the things that virtualization introduced, but, right, when we were first starting to consider putting any type of workload in virtualization, the question is, what's the hypervisor tax? Right? What's the virtualization tax? I'm going to gain flexibility. What do I got to give up? Right? Which is why a lot of folks start to look to other technologies like containers, right? Something that can deliver a layer of flexibility without sacrificing as much performance.
Thank you, Chris. That's an excellent point. I worked for many years at VMware as we were getting more and more workloads onto virtual machines. One workload that always was somewhat out of our grasp was the big data workload, because not only was it CPU intensive, but it was storage and I/O intensive as well. And with hypervisor virtualization, you had to rely upon a vSCSI, a virtual SCSI stack, or a VNIC, a virtual network interface card stack, which meant you were emulating quite a bit of soft I/O, especially for big data workloads. Therefore, enter Linux containers. The value of Linux containers is they give you the same sort of isolation. They allow you to package your software and get much better utilization of the CPU and memory resources on a single box, but they don't require paying that stack of a virtual SCSI or a virtual NIC. Since they're operating system level virtualization rather than hypervisor level virtualization, you use the native stack of in this case, Linux or Windows if you're running on top of Windows to run the container. The OS, as Chris was saying though, we're always looking at how much penalty, when you virtualize a job, how much are you paying in overhead? That's the additional tax that you're paying to run that job for the flexibility that virtualization gives you. And you always want to keep that tax as low as possible. So with CPU and memory, it's quite low with containers, and it's negligible with network and storage. We've done extensive testing of these performance, and it's almost the same whether you're in a container or not in a container. So one more thing which I really liked was when Docker file format came around, we had another great increase, is that you now had a truly transportable package or a box to move your software from one platform to another. If you remember ESX and Hyper-V and KVM, all of them had different, subtly different vDisk formats. So if you had an image that would run on VMware, it wouldn't necessarily run on Hyper-V without a fair amount of work, similarly on KVM or Xen. With Docker, we now have a common file format that can run on any container-based platform. So it's easy to use and to share. This will actually become critical as we want to move our workloads from on-prem into a cloud. Okay, so now I think we have the pieces that we can talk about. We've assembled the pieces of technology that we can begin to talk about big data as a service. Okay, before I talk about what big data as a service is, when we've taken you through the journey of how we started from the Google file system paper, made some technological advances, and where we are now. Similarly, data scientists have also advanced. So when Google had their first deployment of a one monolithic cluster, all they were running were batch jobs, MapReduce version 1. There was no Spark, there was no F-Link, there was no HBase, Hive, Pig, Hue, Impala. What we have now is we have data scientists wanting to run a large variety of jobs. So the richness of the Apache open source community has provided a wealth of infrastructures. But with this, and on the rapid pace of evolution, is you have many different versions, many different types of software. Now data scientists want to have a cluster running each one of those, or multiple ones, and they want to have this type of data and that type of data. What that has caused is a proliferation of Hadoop clusters. It's no longer one cluster in production, maybe, or one in production and one in dev. Now you may have 50 in dev, and you may have 3 or 4 in CI, in continuous integration, and you may have 1 or 2 in production. These become very difficult to manage at a physical level, and so something like big data as a service becomes more and more attractive. So the new realities of how data scientists use Hadoop, what they demand from the Hadoop infrastructure, also leads us to big data as a service. Now, I've often asked, what came first, chicken or the egg? Was the demand first, demand from the data scientists, or did our technology advance? I think the answer really doesn't matter. It's where we are now in terms of what we can give to the data scientist. This is a timeline. I think both Chris and I will try to point out the salient pieces. Back in 2003, we had the Google paper, and we made steady progress. So first release of Hadoop there in 2007. 2002, we had VMware come up. And then we had obviously all the advancements of the Dell infrastructure.
Right. So you can see there in 2009, our data center solutions team, that's that group that caters to that elite few, they start releasing their first purposefully designed big data servers. And again, you had to be a specific class of customer to get them at the time. Right? But as we started to release more and more of that technology and let it trickle down into the general purpose portfolio, if you look, the first time we shipped those boxes, there were 2 models, right? A capacity-oriented version and a performance-oriented version. Those are the 2 models you get. The time when we refreshed that platform 3 years later, there were 8 models, right? Now there are 12 models. And you're going to see each one of those keep growing, each one of those catering to specific big data use cases as they start to arise. Ones that have in-chassis tiering and all sorts of other crazy things that you never would have conceived back in those days of, oh, so you just want more disks in the box, right? At the same time, customers want this to not be a science experiment, and so they look to companies to provide some way to wrap hardware, software, services together in some sort of consumable turnkey service or solution. And that's where we actually saw that initial opportunity there, and we released the first big data solution where you could buy all of that turnkey. Right? And we've actually now just released our 18th refresh of that solution, so we're getting pretty good at it. Right? And there are plenty of other solution vendors and system integrators that are doing the same type of thing, making this a little bit more palatable, because you don't necessarily want to have your data scientists having conversations around optimal core to spindle ratios and RAM sizing. Wouldn't you rather have them talking about what data sets do I need access to, et cetera? Right? And at the same time as we start to get into doing performance analysis and helping deliver the value and demonstrate the value of those turnkey solutions, how we can deliver on our promises, right, and claims.
Thank you. Okay, so just to recap here, all the pieces are assembled. We have fast virtualization with low overhead, fast networking, fast storage. And now we have the demands from the users for rapid number of scalable, versatile Hadoop clusters, and we don't have to sacrifice performance. So now we can usher in the age of big data as a service. Now we've gone this far. We've gone 20 minutes into the session, and we haven't ever defined what big data as a service is. I'm sure everyone in here thinks they have an idea of what big data as a service. I did a Google search, found dozen different definitions of what big data as a service is. Some people refer to it as a combination of data as well as processing and software. I find that personally kind of hard to grasp. I like this definition. It's kind of general purpose, a mechanism for the delivery of statistical analysis tools and information that helps organizations understand and use insights gained from large information sets in order to gain a competitive advantage. It says nothing about how to implement it, but it says what you absolutely need, what you require as an enterprise out of your big data analysis platform. So we'll take this definition, kind of break it down, go through stage by stage. With that definition, there are 4 basic types, and each one of these types builds upon the other. It's core, we'll define each one of these. Core, performance, feature, and integrated, different levels of big data as a service.
So we start with core, right? Core, you think of Amazon, EMR, This is something, or even before EMR actually, this was something where you just took an image, a predefined image, maybe an AMI or some sort of template that had basic Hadoop on it, Apache Hadoop with an OS, and you could just churn those out. You would have some sort of configuration management, Chef Puppet, whatever it is, that would do a modicum of customization, and then you could churn that out. It was as minimal as you can get. It was really just intelligent orchestration, right? Barely an actual as a service, right? Then we start to see where you cater that same type of workload down a little bit further into the stack. And we start talking about down into the stack, we're closer to hardware. And so, okay, well now let's deliver AMIs on servers that have more memory, right? That have more SSDs, that have larger capacity, faster NICs, et cetera, and we can cater each one of those to a different tier and different bill rate, et cetera. It's not providing a tremendous amount of additional configuration at the actual user experience layer, but it can provide some performance, customization, and cost optimization. Right. I'm going to go into feature.
Well, thank you. So feature is just the opposite of what Chris was talking about. So performance, as you look down, you start from the Hadoop distribution, you look down into the architecture, whether it's networking or storage, CPU quality of service. Feature, it's just the opposite, you look upward. So you look at the second tier of applications built on top of a Spark infrastructure or built on top of a Hadoop infrastructure, such as HBase or Hive. And then you go even higher than that, up into a BI tool, business intelligence tool like Datamirror, Platfora. That's the entire stack for feature BDAS. And what that means is that the data scientist says, stand me up a cluster, and I want it to have these 3 tools. So the infrastructure will, in some fashion, install that distribution of Hadoop or Spark and install each of those applications, configure them, and present them ready to use to the data scientist. And more than that, it will also attach data sets to that infrastructure to allow the data scientist to immediately begin operations. And integrated BDAS is the whole thing. It's the whole banana. It's the nirvana of BDASS. It includes very strong and reliable core big data as a service. It requires high performance big data as a service and a complex and complete feature big data as a service. I don't think we're quite there yet, but that's what we're all shooting for in this world, to come up with the perfect integrated big data as a service offering. Now, the $64,000 question, which we haven't yet addressed either, is where is the darn data, right? So how do I get this data into the cloud? Do I even need to get it into the cloud? Can I just leave it where it is in my local HDFS or in my legacy storage device? That's what we'll kind of talk about next. And before we can talk about that, let's just quickly, I'm sure everyone in this audience is aware of private cloud versus on-prem and kind of the trade-offs they're typically involved in whether you deploy on one or the other. Public cloud could be Amazon, it could be Google Cloud, it could be Azure from Microsoft, anything. And what they're offering is it tends to be low CapEx. So it's a low cost to start, but there may be larger amounts of operational costs down the road. On-prem is typically the opposite. Larger startup costs, but perhaps lower operational costs. There's a definition of expandability. I don't like the word infinite because even the public cloud's not really infinite. It has a lot of capacity. Okay, so you can tend to keep using more and more of it. Less secure, more secure. Once again, I've talked to many people in the industry. I'm sure Chris has talked to many as well. Some industries, public cloud is plenty secure. Other industries, no, it's not possible. You have to have everything secure in your own data center. So to me, that's kind of a trade-off. And then to me is the most important one is control, less control or more control. With public clouds, you tend to have less control. You tend to have a limited number, unless you go for something like a platform as a service or something very low level. You have a limited amount of software that you can actually use. It's the set of software supported by that public cloud. Typically on-prem, if you're building it yourself, you can control any type of version of that particular software that you want.
So when we think about that, the perfect nirvana would be able to not have that matter, not have your data where it resides matter. And so what we would like true workload portability. Right? If we had parity between private clouds and public clouds, then we could move that data, that workload, and its associated data to the area that best serves a given purpose at a given time. Right? There's a problem with that, and that's that public clouds tend to be somewhat proprietary. Right? Certainly, the writing a bunch of configuration and automation scripts for AWS is not going to get you anywhere on Azure, and vice versa. The same thing where you have, Azure's built by Microsoft. You can't run something necessarily currently that runs in their public cloud that will also run on their private cloud software. Right? You get very much locked into the venue and the ecosystem that you initially start at, and that's never good. Right? That's lock-in. So what we would love is, we start to see customers adopt things like abstraction layers, right? Whether that's through a big data as a service layer, like we see with Blue Data, and we'll be talking about here in a little bit. Maybe through a platform as a service layer, things like Cloud Forms, Pivotal Cloud Foundry, right? Where as long as you can deliver those set of services, you can code your workload to that platform. Where that platform resides shouldn't matter to you, right? And then the perfect world would also be API-compatible private cloud. And there is a path to doing this, right? Microsoft Azure PAC is getting close, and then Microsoft Azure Stack that's coming towards the end of the year into next year is even going to provide more API compatibility so that you can get that portability. And then we see the same thing with private OpenStack, public OpenStacks, and then VMware Cloud Air. They're providing much higher levels of feature parity, API parity, to facilitate that actual workload portability. But at the end of the day, there will be better use cases for public and better use cases for private, most likely. Right? Anytime, a good example of a public cloud use case would be workload where it's going to be shorter lifespan than 16 months. Right? So there's a study that I cite there. Basically, they took 10 nodes running a public instance of Microsoft SQL Server, and then enough hardware to run the same type of thing, the same resource limits, et cetera, privately. And at what point does it become more expensive to run in the public cloud than it does in the private cloud? So where's my ROI? Right? And they noticed after about 16 months is where they actually diverge from one another. Right? And if you think about that, just like we talked about earlier, Tom talked about earlier, you have your initial CapEx cost when you buy all the hardware. That's great, but a much lower marginal cost. Right? Public cloud, anytime you're paying for everything like that, your OpEx cost tends to be relatively fixed year after year after year. You don't get many gains as you start to get towards the upper end of that 5-year span. When your data is already in the cloud, right, ingress, egress fees will kill you. Right? And so if you can keep your workload there, adjacent to your data, it probably makes a lot more sense to do all your processing up there. Anytime you have public-facing services, nobody wants to go and develop their own content distribution network, right? Might as well leverage the ones that the public cloud infrastructures have already provided, right? Anything public-facing tends to do better out there. Same time, better use cases for on-prem and private cloud, high-performance clusters, right? This is where, like Tom's point earlier, you have full knowledge. You can tune every component in that box. The make, model, revision of your RAID adapter all the way down to the size of your DIMMs and the source of the provider form, right? Data security. And when we talk about data security and data compliance, it's not just, I can't let this information get out. It could be tax domains, right? I can't let this enter a new taxing district, so I can't have it cross lines to get to a public cloud. Right? We see that a lot. We see a lot of that across government lines. Right? I'm not allowed, due to compliance reasons, to have anything stored in a data center where a particular other government has oversight over it. I can't even have my traffic go through a router sitting in your country. Right? Persistent clusters with greater than a 16-month lifespan in many cases. Right? High-capacity clusters. If you start talking multi-petabyte clusters, right, that's going to persist at that type of capacity, you're not going to want to be paying multi-petabyte fees out in a lot of public clouds, right? That's going to kill you, especially because you're going to use that data less and less and less. And now you're literally just paying somebody to store your data for you, right? When SLAs are needed, when a job just has to get done, right? I can't have this contend with anything else on the system. This is critical to the way I do business. This is how I, deliver on my revenue. I have to get it done. It's best to own the hardware top to bottom. So.
Thank you. So we've been talking about big data as a service, as a generalized platform. Now I want to take 2 slides here and talk about an implementation of this. We saw one implementation this morning at the keynote. Azure from Microsoft was showing a type of big data as a service for rolling out the various solutions on Azure. Blue Data, the company I work for, has a product called Epic, which is an on-site solution on-prem for implementing big data as a service on a virtualized environment. It happens to use Docker containers as a virtualization solution, but it could use any one. Self-service, what we try to do is provide the most functionality to the data scientists. Our entire hope is that an IT person would not need to become involved. The data scientists would know enough about the applications they want to install, the capacity, and so forth, so they can just communicate with the Epic system, provision their own cluster. And in this case, we say BYOS, bring your own software. Runs completely unmodified software, so you can bring any version, any application, dump it on the system, and Epic would manage the life cycle of that particular Hadoop application or big data application. Compute and storage separation. We have a technology similar to Tachyon, Alexio, where we can abstract the storage back end and then deliver the data into a Hadoop application where the application itself has no idea. He thinks it's just coming from a local name node or a set of data nodes, a local HDFS file system, when in fact it could be pulled from quite far away on an object store or an NFS file server. What this does is it kind of associates itself with, addresses Chris's issue about the 16-month lifespan of when it's good to go to the public cloud, okay? If you have a private cloud, then you are able to use that existing hardware for more than one application. So if you have a short-lived cluster, like 10 or 12 or 15 months, it can coexist with a number of other clusters and make them cost-effective on your hardware, so you can dollar cost average down or your hardware costs. And similarly, one of the big problems we have found with just taking kind of a simple-minded approach to running Hadoop in the cloud is that you have to ingest a lot of data into a local file system before you can even begin to process the job. Now there's some changes have started to come around. Amazon S3, for example, you don't have to ingest the data, you can pull it directly from S3. But in general, there's a penalty if you need to ingest data into that HDFS file system. And then also we offer a level of secure multi-tenancy where you have VLANs isolate everything. You can use your own Active Directory, LDAP authentication, as well as Kerberos to protect who gets access to what types of data. And so just as a graphic, this is what you would typically see in an enterprise that has not yet adopted big data as a service. They will have a collection of clusters, perhaps by service. They have R&D, sales, manufacturing. All of them tend to be expensive, may be managed by independent IT groups, all of them with very low CPU utilization, typically under 30%, more likely around 18 to 20%. So you have a lot of CPU cycles that are lost. With a virtualization solution or big data as a service, you can reclaim that CPU utilization. I just left Blue Data Epic there, but it could be any other ones as well, any other big data as a service solution. And you can reduce your cluster sprawl, which is what we heard your other IT side, the original side, as opposed to this new system. Now, what Blue Data just announced is moving forward from just an IT or on-prem solution is now we have a solution in the cloud as well. So Blue Data Epic can offer the data scientists the exact same look and feel, the same experience, single pane of glass, whether they're running their containers and applications on a cloud on-prem or on a public cloud. This allows the user to have the best of both worlds, right? They can control their solution, they can control their software, they can package it in their Docker container or Docker file, however they want, and then when they deploy it, they can deploy it in their data center, or they can explode and extend the cluster up into the cloud to take advantage of the infinite resources that are available from a cloud provider. And what we're looking on for the future here is having storage locally, being able to be processed in the cloud, and vice versa, have data in the cloud being processed locally. That's the next generation. That's the next nirvana, is how do we completely disassociate this storage from memory? But that'll be the topic of another talk perhaps next year. Chris.
So where Dell and Blue Data, where we come into this together, we were actually introduced by a collective customer right, in the financial industry. The financial industry finds this particularly attractive because in addition to reducing the total number of clusters you need, it also reduces the total numbers of copies of data that you have to have. If you're in a high compliance industry where you're liable for every copy, every replica that HDFS makes, if I can reduce the total numbers of replicas of my customer sensitive information, that's a net gain for me as a compliance officer. So we had a collective customer come in to us together. We really were excited by the prospect of this. And so we developed a joint offering. Right? We actually tested Blue Data, built it out on some Dell servers, came up with a prescriptive recommendation. We wrote a white paper that you can go out to the Blue Data website or the Dell website and download. It'll give you a guide, a recommendation for configurations of bare metal servers, how you would run this, what results we found, etc. And then you can also come and talk to your Dell representative, your Dell sales representative, see demos of this, or come talk to our subject matter experts at any one of our solution centers throughout the globe. 16 of them distributed throughout the globe, 6 here in North America. All right.
Okay, and I think we have a few minutes for questions here. We have a booth on the floor. If you want to come and see Blue Data, we can show you Epic. If you want to talk to myself or Chris as well, we can do that. Or we can take a few questions now while there's still some time. Sure.
How are you guys working at Blue Data specifically? How are you working with the Hadoop distributions like Hortonworks or Cloudera? So they're spinning up. Are there other licensing models with those guys? You guys are
No, we are not doing a co-licensing agreement. So we use, if we're spinning up a Hortonworks cluster, we'll use the Embari tool to help us spin it up. Same with Cloudera. We'll use the Cloudera Manager tool to spin it up. But that's only the open source software versions that we ship. You'll have to go to Hortonworks or to Cloudera to get the licenses and the support for that software. Sure.
Is there ever going to be a scenario where you'll tie back into like the Yarn community doing as far as like quality of service or measured workload? Will that roll into your software at some point?
Yeah, I mean, we can certainly run Yarn on this. We run it all the time. So and
it's kind of abstracted. I mean, down the line they're going to be controlling IOPS and
we could talk.
connectivity to network devices and things like that. Is there going to be a bleed on what you're doing and what the Yarn community is trying to do right now? Or
I would say right now there is overlap. You're absolutely correct. We are, Blue Data at this solution is plugging in at a lower level. So we're plugging at the infrastructure, the operating system level, where we'd intercept the IOs and do the quality of service at that level. Where Yarn would intercept it a little bit higher, right? So at the Java level, and they're going to do some scheduling at the user space and perhaps go into the driver. But we are trying to be, this solution is trying to be completely agnostic to application. So there might be some one-off or private development with a Yarn solution, but we want to be able to support Cassandra and MongoDB and Flink and any other new technology. So we probably won't do a whole lot of work with focusing on Yarn. Okay?
So if I'm getting this correct, you're a distribution agnostic. You run all of those different.
That's correct. We run with any Hadoop distribution, no modification to the source. So it can be MapR, Pivotal, Apache straight out of GitHub, all that.
And the question to Chris, how many evaluations, POCs, do you run through and big data through your solution centers as well?
Sure, yeah. We, out of the solution centers, we do about 5,000 engagements every year. That's across the entire globe and across the entire portfolio. Of big data, we generally do about 300 or so of those a year. And again, we do all those at no charge. Anybody who's a Dell customer can get the services of the Solution Center at no cost whatsoever. You want to hear about the latest, greatest things from Dell, come see it at one of our Solution Centers. We got one down the street in Santa Clara. You can do that just talking to your account rep.
What's the typical migration path looking like?
From a bare metal solution?
Yeah, if you had bare metal and you wanted to start to work and implement Blue Data.
Typically what they would do is they'd identify what parts they want to virtualize, right? So if they have a production cluster, probably not going to take the risk and do that bam all at once. What you'll probably do is you'll bring in Epic, roll it out onto a private cloud on some additional servers. You can use our data tap technology to connect to the same HDFS as your production server. You can mark it read-only. You can use all Kerberos protection that you want, so only pieces of that will be visible to the, and then you'd probably begin to look at the next generation. So we have plenty of people like they're running one version of Spark, 1.3, and they want to then go to 1.4, right? So they may leave 1.3 in production. They'll run 1.4 on Blue Data and then talk to the same storage, and they'll get comfortable with the process that way. And then so that when they migrate 1.3 up to 1.4 for production, they're much more comfortable, less risk of failure. And so once they become comfortable with Epic and Blue Data, then they'll start to perhaps roll it out to CI level and then up into production level.
Also, maybe couple it with a hardware refresh.
Exactly.
So Broadwell just came out. It was a great time. Build that adjacent cluster to start staging things off. Have that be your hardware refresh and start to move.
That's true. All right, thank you. Time is up. Please, if you want to talk, talk. Thank you.